Hey guys, Buildzoid here, and today we're going to be taking a look at some oscilloscope measurements from the XFX RX9070 Swift OC. I've got the card prepped for measuring core voltage directly behind the core, or well, yeah, relatively directly behind the core. Like technically, the VR, like this is about as far away as you can get from the Vcore VRM. And the reason you want to do that is ideally we would want to measure with the oscilloscope what the silicon is experiencing. Now, unfortunately, it's not really a good way of actually hooking up directly to the silicon, so this is the best thing that I can do. Then for memory, I have that hooked up over here by one of the memory chips. Originally, I wanted to go over here, but there's not really a lot of space for hooking up the probe with these dangly wires. I'm not really a fan of that. This thing over here is a little current sense amplifier, which I'm just using to... so normally, like, this is meant to measure the voltage drop across a shunt resistor, but you can also use it to measure the voltage drop across a GPU's power plane. So that's not super accurate because I don't know what the resistance of the power plane is, and even if I did know what the power plane resistance was, that would only be relevant at like one specific temperature because copper's resistance changes quite significantly with its temperature. But regardless of how inaccurate that is, it is still very good for getting a rough idea of what the GPU is doing, because if there's a large amount of voltage drop across the power plane, that means the GPU is pulling a lot of current. And if there's not a lot of voltage drop, then it's not pulling a lot of current. So, yeah. So that's what that is. And the yellow line for that is just the power supply, because, yeah, like I have a 5-volt linear regulator on there, and that's fed off of 12 volts. And the reason why it's set up like that is because technically, like, I could have been stealing the 5-volt supply from the GPU itself, but I prefer having its own 5-volt regulator for convenience, because, easier to just have, like, it's much easier to find a 12-volt source than it is to find a 5-volt regulator somewhere on a board, or like, pads for 5 volts. So, yeah, anyway, and then for the power rails that I don't consider so important, that being Vddci and Vsoc, I just have coax soldered directly to the card, which, honestly, I would have preferred to just solder coax directly to back here, but you might have noticed these capacitors are very small. And like, it is technically doable, but I don't like soldering coax directly to very, very small capacitors like this. Like 0603s and 0805s, if there's like a bunch of them in a row, then sure. But this, no. So yeah, like this, like getting these little wires in there was already annoying enough. I don't feel like dealing with trying to squeeze coax in there. So, yeah, so Vddci is just direct coax, and Vsoc is also direct coax. It's worth noting that the SoC VRM is a 3-phase, and 2 of the phases are over here, and 1 of the phases is over here. So this measurement, well, it'll make, like, the reason I'm pointing that out will make sense once you see the measurement from the SoC power rail. And yeah, this is not ideal. Like, ideally, we'd want to be measuring SoC power directly behind the core, same with Vddci, but yeah, that's really that's really inconvenient to hook all of that up. So, yeah. And also, I just don't care about getting as good a measurement for those 2 power rails. So, anyway, that's how things are hooked up. The first power rail that we're going to be taking a look at is Vddci, because there's not really much to see there. So, yeah, it's also worth noting my card does not have a power limit. I've modified it to disable the power limit. So, yeah. Anyway, we're just gonna... Okay, so now it's not gonna go idle, is it? Wait. Oops, wrong mouse. Yeah, so what's kind of crazy with the 9070, and I guess maybe some of the older AMD GPUs were already doing this, but this thing has, like, crazy amounts of power savings on every single power rail. Like, I remember back in the GDDR5 days, like, you had a bunch of voltage regulators on the cards that would just sit at a constant voltage regardless of what the card was doing. Yeah, but on this card, like, you can see right now, Vddci is actually just completely turned off. Right? Like, it is actually just off. Also, the reason why it's reading a little bit below 0 is because of just how the wires are hooked up. So not entirely, like the way this is hooked up right now is not ideal for getting perfect DC voltage levels, but yeah, that's not really a priority for me with these measurements. So anyway, so yeah, you can see that Vddci, like if it's not doing anything, it just gets completely turned off, which is kind of wild, because a lot of like the GPUs I'm used to, the Vddci rail does not turn off. But anyway, so let's actually run some load on this and take a look at what it looks like. Now, the reason we're starting with Vddci is there's not really much to see. We're going to start with just GPU-Z. Did it open up twice? Man. Anyway, and if we actually run a render test, you can kind of see how because the thing with GPU-Z is this render test is very, very light, so it like barely gets the GPU core to do anything, which you can see from the blue line is the measurement from the current sense amplifier. So yeah, you can see that that's like a very small amount of current that the GPU is pulling. So you can see slight deviations in the Vddci voltage because of that, because obviously when the GPU is actually rendering something, the power consumption goes up. I'm actually not sure how it's working out right now. Oh, I was kind of hoping it would just... It's kind of doing the opposite of what I figured it would do, which is... Because the thing is, I think every single power rail on this card does have V-droop. At least all of the ones we're measuring have V-droop. So my assumption was that this should have actually gone down a bit instead of up. But then again, I guess since we're measuring at the voltage regulator instead of behind the core, it might actually be because of like the resistance in the connection between the voltage regulator and the core that the voltage is going up a bit. Anyway, if we zoom in on this, we can kind of see that, yeah, it's not really... Like, the amount of capacitance on the Vddci power rail is not entirely smoothing out the actual switching of the voltage regulator itself, as we can clearly see every single PWM pulse. Now, it's not, huge peak to peak or anything, but the GPU also isn't really doing anything right now, and I think we're in, like, the low power state for the Vddci power rail right now. So, this is a little bit disappointing. I mean, it doesn't actually affect the operation of the GPU, but yeah, I'm not really a big fan of being able to see the actual like switching function, like the switching behavior of the phase directly from the output. So that's that. Anyway, let's run some 3D Mark. Put some stress on the memory controller. This is not really shuffling any data around, just running the GPU-Z render test. Now, do I have this crazy fan profile set up? Because I do not feel like having that kick in. Oh. Oh yeah, we are on the manual fan profile. That's not ideal. There we go. Now let's run some time spy. Oh, we're still at 200 microseconds. It's really small. Okay, there. So now you can see Vddci actually running. And you can basically see how, yeah, now that the memory controller actually has work to do, like, first of all, we're running at 850 millivolts instead of, like, 650-ish, which was, like, the low power state for the memory controller. And also, yeah, this is much more of a net mess, though I think this is going to be a pain to trigger on. Yeah, it's just not gonna, is it? Okay, there we go. Yeah, you can kind of see, so basically here the GPU is pulling a lot of current, and this is, I believe, the GPU waiting for memory access. And you can kind of see how that correlates with the behavior over on the memory controller a little bit. It's not super, yeah, it's not super clear. You know what? I should have put the trigger on the actual, well, that's also not really going to work because there's a bunch of noise. So I don't know what I'm expecting. Yeah, that's also not really going to do what I was hoping for. I mean, it is easier to trigger on it, but it's not like we can see much of anything. Well, you can kind of see some things that look like they might line up, but yeah. The main thing is that you can still see very clearly the switching waveform of the voltage regulator. Though it didn't really get any worse, but yeah, like, I think most of what we're seeing in terms of peak to peak here is probably just effects of the resistance of the power plane for the Vddci rail. So, yeah, the Vddci rail, like, I don't really see anything wrong with this. I mean, I've seen Vddci rails that are lower peak to peak than this, but, like, this is fine. Probably one of the reasons why you see a lot of why some of the 9070 XTs out there will actually like cut down on the amount of capacitance for the Vddci rail. Funnily enough, the card we're looking at here actually has 3 bulk capacitors for Vddci, whereas there are some cards that only have 1. But yeah, like it makes sense to me that there are some cards where you only get 1 because it's not really there's not really anything like much to worry about on the memory controller power rail. So, anyway, you might also notice that my score is abnormally high for a 9070, and that's because I don't have a power limit. Like, we're at stock clocks right now, and yeah, there's no power limit, so that's what's going on with that. Anyway, let's switch to a power rail that's actually somewhat more interesting to look at, which is going to be Vsoc. Now, Vsoc, I believe, actually runs all the time. It doesn't go to sleep. So, oh, I guess we missed the turn on transient, but that doesn't really matter. It's not like there's much to see there, at least as far as I'm concerned. Let's switch the trigger back to channel 1. And yeah, so the SoC power rail is, like, it does have power savings, whereas in it'll change voltage levels depending on what's going on, but it is a lot noisier than the memory controller power rail. And also, just like the memory controller power rail, we can see the switching action of the voltage regulator, except what you're going to notice is that we basically, because this is a 3-phase, right? Except we're measuring from 2 phases instead of the third one, because the third one is on the other side of the board, right? So if we look at the photo here, yep. So we're measuring over here, and you get like you get 2 phases for VSOC over here. The other phase is all the way over here. So when you look at the waveform, what we're seeing is basically phase 1, 2, and we're not seeing the third one because that's on the other side of the board. And then 1, 2, and the third one's on the other side of the board. 1, 2, third one's on the other side of the board. You get the idea. So, yeah. But also, there's not really... Like, the thing is, there are GPUs out there where if you try to measure directly at the output of the voltage regulator, you basically get, like, a flat line. So, this is a little bit disappointing, but at the same time, it doesn't really matter as far as I can tell. So, yeah. Like, there are tolerances for how the GPU's power delivery is allowed to run, and this is within them. And I think right now what we're seeing is some phase shedding in action. Like, you might be noticing that there's even less pulses. Oh, yeah. So you can see, so basically, this is the voltage regulator, like, not running all of the phases, and then here they kick back on again. So I guess I must have, like, touched the mouse when I was messing with the scope. But anyway, I guess we'll just start with GPU-Z again, and then we'll run some time spy. Though I don't think we're going to see much of anything in GPU-Z. Yeah, we don't really see much of anything. Well, I guess... Let's see. We do see a little bit more. Well, let's try scale this. No. Get the trigger onto channel 4, and I'm going to try to trigger off of the actual frame render. So you can kind of maybe see that there's like something happening here, but we can't really tell what's happening, right? Unfortunately, I don't have another current sense amplifier hooked up. Though I don't believe I bought like 5 of them, so I guess I could have built a couple more. Actually, I could have probably just built like a multi... Yeah, I could have just had a bunch of them on the same board. I don't know why I only built the board with one input. Because that 5-volt regulator will run like, I don't know, 10 of them or something. So yeah, I guess we could have also had like current sensing for Vddci and Vsoc, but too late for that. So yeah, but unfortunately there's not really much to see in GPU-Z as far as I'm concerned. So let's run 3D Mark Time Spy again. And kind of see the power management doing its thing with the SoC voltage going up and down. I'm going to drop this back down to 1 volt so that it doesn't take up the entire screen. And actually, I'm not sure if we need to move this up because it's going to go up in voltage once we're actually running Time Spy. Now, the interesting thing with the SoC voltage is actually depending on what memory clock you're at, it'll be higher or lower. So if you overclock the memory, the SoC voltage actually goes up, which is kind of interesting. That doesn't happen for any of the other power rails, as far as... Like, I've obviously pre-tested this, and I'm relatively certain that Vddci does not change based on memory clock. It's just SoC, which might be because, like, an internal... Like, I'm assuming that raising the memory clock is affecting, like, the Infinity Fabric clock or something. Oh, yeah, so there's Time Spy. Very, very noisy, right? And this is why I was like, oh yeah, Vddci is not a big deal because sure, Vddci wasn't, you know, the 30 millivolts peak to peak that we saw at idle. But this is 120. So... And you can still kind of make out the switching waveform, but there's like actual big like power transients in there, right? Like the big spikes is just, that's not the voltage regulator, that's the... that's like whatever the SoC power rail is powering, that's what's causing the bigger spikes. And those, like the way we're seeing them is actually not super accurate because we are kind of far away from the actual silicon, right? With where the probe is hooked up. But yeah, so the SoC power rail, pretty noisy. And you can actually kind of see how it like lines up, like when the GPU is actually at high load and running a full like frame, like when, yeah, when the GPU core is actually like crunching a lot of numbers, the SoC power rail actually gets pretty quiet. And then I'm assuming this mess is mostly like memory manipulation stuff going on, or like memory, like data getting shuffled around. Because basically my understanding is like we have like data getting prepared for the render, or like the bulk of the work happens here, right? Which is why the current draw is very high and constant. Also, these big spikes that we're getting on the current sense amplifier, I wouldn't consider them super accurate because there is a lot of noise on the Vcore power rail. So I did consider actually putting like a filtering stage in front of the current sense amplifier because well, once you see the Vcore power rail, you'll see why I don't think like a lot of like these spikes I think are more like the like they're more the switching noise from the GPU core rather than like actual changes in the current across the power plane. Whereas this right here, this is relatively constant, so that's just like okay, the GPU is actually pulling a lot of current right there. But yeah, so what's kind of interesting to me is that you can see that the SoC power rail is noisiest when we're in this sort of like not actually running a lot of number crunching on the GPU state. Um, right, so I think this is basically like data getting shuffled around, and then we have like the bulk of the work getting done. But I could be wrong about that. Um, anyway, so that's the SoC power rail. Actually, no, we're not done because I did want to show you the voltage changing depending on what memory clock we're running. So actually, I wonder if we could do that with 3D Mark running in the background. Because that'll be more interesting in my opinion, if you can just see it happen as we change the clocks. And this should be fine. And like some, like, changing clocks on the fly, like technically the GPU does that when it just goes from idle to 3D and when you tab out and that kind of thing. But we all know that like sometimes when you tab out, like on certain drivers with some GPUs, if you tab out of a game, there's a chance the GPU will crash, right? So, yeah, but it should be fine to just change the clocks on the fly. And for this, we're going to run, we're just going to keep running Time Spy. The thing is, like, Time Spy's render test, especially the first one, is not super consistent in terms of the load. And windowed and looped. Hopefully we're not gonna run in. Well, I guess I can just like switch back and forth between the windows. Hello, could you run? Okay. Anyway, so right now we're running at around 830 millivolts, as you can see over here. And I do believe, yeah, and that's not changing. We're 830 millivolts average. And now if I raise the memory clock to say 2600, you can see that we went up to like 850 millivolts. Also, this is not running properly. Yeah, okay, so windowed mode for Time Spy apparently no worky. Fire Strike, GT1. Actually, GT2 is probably better for this because that test hits the memory more than GT2. Well, than GT1 does. GT1 like absolutely hammers the core, but GT2 is more about memory. So anyway, let's start with 250. There we go. Now it's running properly. So, yeah. So we're averaging 840 millivolts. Yeah, so that Time Spice test was just messed up for some reason. If we go up to 266, yeah, you can see how the memory voltage, or I mean the SoC voltage is like going up. I mean, there's like specific intervals when it happens. Yeah, so now we're at 870. 900 almost. Now, the GPU will, like, it'll get unstable if I push it past much past 2800, so I don't think we're gonna see. Yeah, now it's at 900, and it is still running, but at this point, the GPU should be losing performance because of the error correction kicking in. And then 2840, and I crashed it. Yeah, but you can see how basically, so at stock clocks, the card basically runs at like 800 to 850, and then at higher memory clocks, it actually runs all the way up to like 900 millivolts. Which is interesting, because off the top of my head, I've never seen that behavior on any other GPU. So, yeah, that's kind of interesting that I'm assuming AMD just coded that behavior into the driver or something. Because unless, like, there's... Nah, it doesn't really make sense for that to be in the GPU BIOS. So, yeah, I'm assuming that's just tied into the GPU driver. Apparently, I crashed it really hard. It's not recovering. Well, that's fine. I was going to power down the system anyway so that we can switch probes. Oh, it's not going to want to shut down now, is it? Okay, well, now we're going to take a look at the memory power rail. So that just shot off screen because even at idle, GDDR6 runs at 1.25 volts. I mean, for boot up, it boots at like 1.3 something, but once it's up and running and we're in Windows and we're idling, it should drop down to 1.25. That is lower than I think it should be. I wonder if there's something wrong with the connection, because under load it should be 1.35. Now, interesting thing with the memory power delivery, is that GPU-Z doesn't kick the memory into 3D. So, like, the memory power delivery, where it literally just doesn't... And the crazy thing is, that happens even in some old, like, 3D benchmarks. Like, 3D Mark 11, some of the tests will not boost the... Like, will not get the GPU memory into 3D mode. So you can actually see, like, the core will be running at pretty, like, high voltage, but the memory will still be at idle state. Which is kind of weird. Anyway, I'm assuming the GPU driver reset itself, right? Yep, it completely reset itself. Okay, that's good. Now, the memory doesn't get its voltage boosted based on, like, what frequency you're running it at. Yeah, let's just run Firestrike this time. It doesn't really, like, the thing with the different 3D benchmarks, like, they do technically have different noise patterns, but it's still ultimately noise. So, there's not really much I can tell you about it, because I don't know what it's actually doing at any given moment. Yeah, so now we're averaging about 1.34 volts, which some of that is going to be, like, I am running, you know, passive probes, and some of that is going to potentially be the fact that I'm measuring from a memory chip that's relatively far away from the voltage regulator. So, yeah, and also because of that, if we actually, like, we're not going to be able to see the voltage regulator, like, switching noise in the memory power delivery. Because it's too far away. I mean, you can kind of, you know, you get that waviness in it, but it's not You know, it's not like the VSOC or the Vddci measurements, because both of those are taken like right off of the voltage regulator, whereas here we're like halfway down the board near a memory chip. Actually, we're more than halfway down the board. Like we're about as far away as we can get from the voltage regulator. And the memory power delivery on this card, in my opinion, is a bit on the noisy side. At the same time, I don't really think it matters potentially, because I did mess around with like raising and lowering the memory voltage, and that didn't do anything. Well, okay, no, that's not true. It made the performance worse. So, um, well, you know, if changing the memory voltage makes it worse, then the memory voltage not being super stable might also make the performance worse, because that might be triggering like a little bit of error correction when you're right on the edge. Um, so I don't know, maybe knocking this down, because there are high-end GPUs out there where the memory power delivery will be like 40 millivolts peak to peak. Mind you, we're on 20 megahertz bandwidth instead of like, ideally I'd want to be on 100 megahertz, but in pre-testing I found some like weird noise getting into the measurement, and I couldn't figure out where it was coming from. Usually that kind of thing is because you run the probe too close to a switching regulator, so you just get a bunch of switching noise dumped into the signal. Um, and by that I mean, like, if you run if you put coax right behind right next to the switch node of a power stage or something, like, the turn on transient of that power stage will actually produce enough EMI to like dump, like, you'll actually see it in the coax measurement. Like, it'll actually get through the coax. I have a video complaining about that when I was trying to measure a motherboard. But yeah, so I ran into the same issue here, and I couldn't really figure out where it was coming from because the probe isn't really near anything. With the motherboard, it was super obvious. I ran the coax like right over the Vcore VRM, so it's like, yep, that's where that came from. But here the probe is kind of floating in free space, so I couldn't really figure out where the noise is coming from, and that's why we're on the 20 megahertz bandwidth limit. Because I don't know, like, it might have been real, but if it wasn't real, then it was a problem. And so, but the point is, I've measured some like high-end overclocking GPUs in the past, because reference cards are generally pretty horrible. But like Lightnings, EVGA classifieds, that kind of thing, Asus Matrix cards, and those can sometimes get like the memory VPP down into like the 50 millivolts range, even on 100 megahertz bandwidth. So this being, 70-ish on 20 megahertz bandwidth is a bit of a disappointment to me. At the same time, I'm not sure if it actually negatively affects the performance of the GPU. So, yeah. So it might just, like, may very well be well within tolerances of the, operating, like, well, yeah, it might be in the operating tolerances of the memory controller and the memory chips, and so, a GPU that then goes out of its way to, like, have better power filtering for the memory power delivery might not actually translate into better performance whatsoever. In which case, that's just, like, unnecessarily inflating the manufacturing cost. And I also have some modified GPUs that have their memory power delivery down in like the 30 millivolt range, but those are modded, so that doesn't count in my opinion. Like, yeah, so 80, and now like in TimeSpy we're getting like 80 millivolts peak to peak. So yeah, I think this is, like, it's not the worst thing I've ever measured, but I'm not impressed by this. It's better than the SoC power rail, but yeah, like, it better be, because the SoC power rail is kind of like a secondary Vcore rail in my mind. Whereas memory chips and memory controllers usually aren't super hard on the power delivery. So, yeah. Anyway, so that's like most of the like stuff that I wanted to show you with the memory power rail, which is that There's a lot of power savings on it. But it's also kind of noisy. Oh, and actually here we can really see the sort of like, this is where the GPU is doing all the work, and this is where the memory is doing all the work. Right? Because here, like when the GPU is under high load, the memory voltage is smooth, and when the GPU is like, I'm still assuming this is like shuffling data around. Yeah, the memory power delivery gets stressed out. I mean, to be fair, the GPU power delivery during this section right here also gets very, very noisy. But it's, well, so it's not really that interesting, I guess. Is basically what I'm realizing is like, yeah, of course, when like I really, the thing I'm wondering is like, I wonder what the I wonder what like the memory usage looks like during one of these benchmarks running. Like what is actually like what kind of memory requests is the memory handling? Um because I'm assuming when we get that like constant like state of high load on the GPU core in between all of the noise, the memory is basically not doing anything is my assumption. Um right? So like the like read write operations would drop to like 0 temporarily. Or maybe not. I don't know. Like it could also be that it's just like constant load on the memory at that point. Um, but I have no idea because that is just one thing that yeah. Um, I don't know. Anyway, so now we're gonna take a look at the core power delivery. Um, Now, when you boot one of these cards, what's kind of crazy is the core voltage doesn't even turn on. Like, see? Literally, and then once like Windows starts, the core actually turns on. So basically all of the like basic functionality like display output, I'm assuming is actually running off of the SoC power rail or one of the like the thing is these cards have Vcore, Vsoc, Vmem, Vddci. There's the 1.2 volt rail, the 1.8 volt rail, and the 0.77 volt rail. And then there's like another 1.8 volt rail if you have an XT. But so at a minimum, you have like 7 different main power rails. And so like, I'm assuming like basic display functionality is handled entirely by the SoC power rail. And then maybe some of the other minor ones, because I'm assuming those are primarily for like driving the actual display signal or something. Yeah, so when you're not doing anything, the GPU core literally doesn't, like the main core power rail is literally completely turned off. Which is kind of cool. Anyway, if we run something like GPU-Z, unlike the memory, GPU-Z does actually get the core to like wake up a bit, but not much. Right, you can see that the core is running at just like 600 millivolts, 700. And we can also very clearly see that this card has VDroop on it. Because if we stop this, you can clearly see that we basically have low current, high voltage, high current, low voltage. So yeah, this has VDroop. If this was an NVIDIA card, what you'd get is basically like your average voltage would stay constant, and this would basically just turn into a lot of noise right here, and then it would flatline, and then a lot of noise and flatline. But yeah, like AMD GPUs have had VDroop for forever, so this isn't really that surprising. But interesting considering that Ryzen CPUs run very, very shallow load lines, whereas this runs a pretty deep one, as far as I can tell. Like, AMD Ryzen CPUs are closer in their core voltage behavior to, like, NVIDIA GPUs than they are to AMD GPUs, which is a bit weird. Like, there's nothing wrong with that. Like, they're fundamentally different silicon, so yeah, they're going to have different ways of dealing with power management, but I find that very interesting, because I would have figured that, like, at this point, AMD GPUs would behave very similarly to NVIDIA GPUs, because the CPUs do, but they don't. So, yeah, anyway, the core power rail is a horrible mess. If we run TimeSpy on this is, like, to be fair, this is not the worst measurement I've ever seen on a GPU. That belongs to a GTX 980 Ti that had a that I repaired after it had, like, a catastrophic VRM failure that I'm pretty sure cooked, like, a bunch of its output filtering capacitors. Anyway, so now we're at 5 milliseconds per division. You can see the power. Oh, I'm gonna have to slide this down. And yeah. Yeah, at 20 megahertz bandwidth, getting 330 millivolts peak to peak is not very, like, it's not the worst thing I've ever measured. This looks like an NVIDIA GPU. But yeah, I'm not impressed. With, like, the same measurement methodology, I have cards that get, like, well, admittedly those are very low power cards, much older, so, you know, they don't have as big power transients as modern GPUs do. But, like, there are GPUs out there that'll be like 100 millivolts peak to... Okay, 100 millivolts peak to peak is actually extremely good, but like 150. So, like, half of what we're seeing here. So, yeah, the Vcore power rail on this thing is incredibly noisy. Now, I don't know if, like, better core voltage regulation would significantly improve overclocking headroom. I still need to test that. There's not really... It's not like I have a magic, reduce VPP button for the GPU. But I do plan to basically just, like, strap a bunch of extra capacitors to the card, and that'll hopefully... I mean, in my experience, at a minimum, what it's going to do is it's going to crush the overshoot, right? Because you can see that, like, these peaks that we're getting, those should get a lot shorter if you just throw more capacitors at the problem. Now, the thing from an overclocking perspective, these upward spikes actually don't really matter, because the GPU doesn't crash if the voltage gets a little bit too high when it isn't doing anything. Nah, the GPU crashes when the voltage gets way too low when the GPU is working really hard. So, yeah, and the downward spikes are the ones that I'm not so sure there's much I can do about those. I'm hoping that I can do something about those, but I don't know. Because those should be the ones that actually affect overclocking quite significantly. But yeah, the massive upward spikes are basically, like, those happen basically anytime the current draw drops, right? Like, you can see here, current draw drops, voltage goes... Well, actually, this is the load line doing its thing. And then we have this, like, random spike, which I'm not sure... Like, the issue with, like, say, this spike right here is, like, I don't know if the current draw actually dropped for certain, or if just that... Actually, it had to. So, yeah, but I don't know how much. But, like, so yeah, you can see from the current sensing that current draw drops, voltage shoots upwards, and then it loads right back up, and it actually doesn't really undershoot because the current draw came back up to basically the same level that it was before. Trying to find a... The annoying thing with this is getting, like, a really specific event, because I don't really have, like, control over how much power the GPU is pulling on a let's see, like, you know, we're at 100 microseconds per division. So like this event right here is like 170 microseconds long. I don't have control over that. Okay, I can't tell the GPU, hey, I want you to, or like this high current draw situation right here. Like I don't have a way to tell the GPU, hey, I would like you to please pull a lot of current for 150 microseconds and then don't pull any current. And honestly, I don't even have a way of doing that at like a millisecond time scale because I am not a GPU programmer. I have no idea how to get the GPU to do much of anything really. So, um, yeah, that's kind of, you know, that kind of sucks. Because I guess if you knew enough about GPU programming, though, I think you'd basically need to be like an AMD driver developer to have that fine control over what the GPU is doing in order to be able to like cause very specific load scenarios on demand. Why is it running windowed? Oh, I didn't loop it. Hopefully it doesn't run. Anyway, I'll try to catch undershoot. Um, oh, it's not running properly. Yeah, so windowed is apparently broken for time spy. That's fine though, because I didn't want it windowed. I just wanted it looped. I'll try catch an actual like undershoot event, like a clean one. I'm in pre-testing. I did occasionally manage to get some that were like, oh, you can actually tell what's going on. It's not just a bunch of random noise, but it's kind of rare. Okay, let's just try our luck. Well, that's a bunch of random garbage. More or less the same thing there. Yeah, this kind of works. By that I mean like this section right here. Though that's like, well, you basically get an inversion of like that's the thing with the voltage waveform is the current sense waveform is basically in like the reverse of what is happening to the core voltage on the card because this has V droop. If this didn't have V droop, then the uh core voltage would basically be doing like a doubling of what the current sensing is measuring. Where it would be like you wouldn't just be getting like here we get an upward spike, so you get a downward spike, but we don't get an equally tall upward spike afterwards. Or like actually we wouldn't get that here. Need a different. Well, I mean this kind of illustrates that. Kind of. Well, not really. Unlike CPU power delivery, GPUs are just incredibly noisy. Well, to be fair, if you run a very like choppy workload on the CPU, you can get similar stuff. So what I mean by choppy workload, I mean something that is constantly like it is very multi-threaded. It can load all of the cores. It's probably AVX, but it also has like constant memory bottlenecks. Um, so it might be easier if we go. Oh, there we go. That's like somewhat intelligible. You can really see the load release overshoot over here, right? Because we go from like pulling a lot of current to basically zero. And then it just shoots upwards afterwards. Um, though when the current draw, well, you kind of get that undershoot over there. So yeah, that's what power delivery looks like on a relatively budget 9070 PCB, in my opinion. Yeah, like I'd say budget because this card, I mean, this wasn't literally the cheapest card available at launch, but by the time I decided to buy one, this was the cheapest one available. So, you know, yeah. And the other thing is like you can see that XFX had the option to include a lot more capacitors. They just didn't. Um, Luckily, like adding capacitors is actually very easy. So we'll see if actually like populating all of these unpopulated capacitor pads actually makes a difference. I mean, again, like I mentioned earlier, it'll probably knock the overshoot down, but I'm like, when I say makes a difference, I mainly care about like, I want higher scores in 3D Mark. As of right now, I'm kind of hitting a wall at around 32,700 points on this card. I'd really like to get it past 33,000 points in TimeSpy GPU test. Like in the in the GPU score of TimeSpy, I'd really like to try get this card past 33,000 points. Um, but yeah, so far I have not managed that, and I'm kind of hoping that maybe somewhat better power delivery could help, but who knows? It might not make a difference. Though it might make a difference. Like, I don't know. Like, this is the thing that I need to test. Unfortunately, like on a lot of cards, I think like, it kind of depends. On some cards, like if you start with a card that already has very good power filtering, adding more capacitors doesn't do anything, right? Because there's sort of a upper limit to how good things can get, especially because ultimately we care about the like what kind of power delivery the silicon itself is experiencing, right? So it's like, okay, you know, the measurement on the PCB of the card might look really, really good, but that doesn't necessarily mean that the silicon is experiencing the exact same thing because there's a bunch of solder balls in the way. There's also the GPU substrate itself in the way, and then the various metal layers of the silicon itself, right? So, um, but reducing the like improving the power delivery at least on the PCB side of things can help on the actual like GPU end of things. This isn't a motherboard. Motherboards unfortunately kind of hit a bottleneck really quickly because CPU sockets are kind of horrible for power delivery. Um, but yeah, at the same time, it's not like I'm expecting, like, even if I populate all of these capacitor pads, I'm not expecting, like, some huge improvement in terms of performance, right? Like, I am talking about pushing the card from scoring, what is it? Let me pull up the calculator. Um, you know, I am talking here about, is this not set to the calculator? Oh, it's not set to the calculator right now. Anyway, so I'm talking about pushing the card to like, I don't know, let's say 33,200 points, you know? I think that would be pretty cool. And right now I'm maxing out at around 32,700. Yeah, that's a 1.5% improvement in performance. You know, so I'm not saying this like what I'm going to do makes sense. It doesn't, but I want to do it anyway. Because I just find it interesting. So, yeah, and honestly, 1.5% is more than I was expecting, because honestly, I've gone to great lengths on certain GPUs for just 1%. Um, but yeah, so anyway, so that's what the power delivery looks like on this here XFX Swift OC card. Admittedly, with the power limit completely disabled. Normally, the card has a 240 watt power limit. Mine has none. Actually, I'll just show you how much of no power limit I have. So if we run TimeSpy again, and not looped, and we'll just run GT1 and 2. And I'll just do it this way. We're going to first run it at minus 30% power limit, which normally would make your card slower, but because my card is modified to not have a power limit, right? So, as you can see, I've set the power limit to minus 30%. Actually, at this point, we don't really care about the oscilloscope measurement. It's kind of funny though with the like to me what's a bit funny with the oscilloscope measurements is like ultimately when I'm actually like modding a card, the only part I care about is the measurements. So this stuff over here, I don't actually like look at the waveform because with GPU power delivery, it's just a mess, right? So it's like there's not really anything for me to see there. Um, but actually, you can kind of tell that the power limit didn't do anything because the card is still running at around 1 volt on average. Um, but yeah. Like, this is still going to get just under 29,000 points, is what it should be scoring. Which a stock 9070 on the stock power limit gets around 27,000 points. Like 27,500, I think, was what I had on this card before disabling the power limit. Um, I really do wish I had managed to put a switch on the, like, well, the issue isn't putting one switch, it's putting two switches. One switch wouldn't be too much of a problem, but like once it's like, oh, I need to find space for two separate power limit switches, that's when it gets annoying. Um, so yeah. Unfortunately, I have the card in like permanently not having a power limit mode right now. It's not exactly hard to undo that modification. It's just like, yeah, kind of limits me on what I can do in terms of showing the behavior. That's the one upside to the 12 volt high power cards is that they only have one current sensing circuit instead of two separate ones. Or like, yeah, like so well, technically this has three current sensing circuits, but only two of them are actually important because those are the ones that monitor the main power rails. I don't really see any point in like disabling the power monitoring on the PCIe slot because the PCIe slot, as far as I can tell, doesn't really power anything all that power hungry. Um, anyway, and this should get still just about 29,000 points. Yeah, just under. So, and that's with the power limit set to -30, and if I set it to +10, it's going to make zero difference because the card has no power limit. And actually, the other way you can check is that if we go into hardware info, and this I'm actually kind of happy about, is that, because I was really worried with the 9000 series that AMD would like double the power limiting, because on older AMD cards, the power limit was enforced by the voltage controller. But now there's separate circuitry for enforcing the power limit. And I was kind of worried it's like, oh, there's going to be a power limit on the voltage controller and another power limit on the power monitoring circuitry, and it's going to be like double power limits. But no, there's just one, which is the total board power limit. Um, and if we run this again, what you're going to see is that the like total graphics power is way higher than the total board power because I've disabled the board power monitoring on the card. Anyway, we don't actually need to run this for like a full loop. That should be enough. And so yeah, now if you look at the power, right, you can see total graphics power 272 watts, total board power 16. So yeah, and you can see that the core current was 205 amps. So this is accurate. I've not yeah, like that is accurate. Well, I used to also have a modification for like changing the current sensing of the voltage controller itself, except that made the voltage regulation even worse because it affects the load line slope. And also, I found out it's not necessary. Yeah, like you just need to disable the board power monitoring, and then the card doesn't power throttle. Technically, we do have this like GPU core TDC limit, but I've not managed to hit that. The card will overheat before it pulls 330 amps. I guess maybe if you tried to run something like Furmark, but personally, I don't like Furmark, so I'm not going to test that theory of like, oh, if you run Furmark on this, it might actually hit the core current limit. Because, yeah, what's the point in doing that? But, yeah. Anyway, that's it for the video. So hopefully you found this somewhat interesting, because I sure as hell don't think it's particularly useful. But yeah, so that's that. Thanks for watching. Like, share, subscribe. If you like the content I produce, there's links in the description you could check out to like support the channel. That would be very much appreciated. And that's it for the video. So thanks for watching, and goodbye.